So if a program assumes a particular DLL file is available, what if that file is not available? Is this program still working correctly? Right? It won't. So you have to test what is the kind of behavior of a program if a particular DLL file is not available. So an attacker may try to block access to such important library files, okay, and make the program not to function normally. So as a programmer, when you develop your software, you should have some alternatives. You should not assume that these files are going to be available. You should have some kind of alternate block of code in your software so that it can still function normally even if certain library files are not available. Okay? So that's what these category of attacks are. Okay? Similarly, manipulate registry values. So the registry, normally you deal with Windows operating system, right? So when you typically say install, say, some software, okay, you will notice that some updates are done to the registry about the installation that you just did. Okay? Say for example, you want to access the software using username and password. The username and password that you sign up for will be stored in the registry. Okay? And typically, the users don't touch the registry or manipulate it that much because they will be scared if they do something, the system is going to crash. So they have the tendency of not to play much in the registry. So with that notion, the developers try to save those values, say for example the password or the license key of all the software you're using, in plain text, which means it is stored something that anyone can read. So if I open up the registry file, say the license key of the software may be stored in plain text, okay? Or certain sensitive information may be something that's directly readable. And so, because developers assume that nobody is going to open the registry file and read them. Okay? Someone told me that I was thinking of buying a commercial version of the software because the trial version was about to expire, but they said just change your date to an earlier date, they won't detect that the trial version is expired. Okay, so that again what happens, because the software is programmed to check for the system date, right? So the system date is still within the trial period, it won't complain about it. Right? So if a user can change the system date, then he can keep on using it forever for free. Right? So that's another drawback. So as when you develop such software, you have to really take care of all these things. Okay? So you cannot believe or trust. Okay? So that's the word you have to use. You cannot really trust on anything. So normally developers write the programs in such a way that they believe whatever they read from the registry. Okay? So you should not really take it for granted. Similarly, when you get inputs, you normally get inputs from the user, right? Your end user can enter input for some values as you write the program. But sometimes you get input through files. You read from the file, process whatever you read from the files in your program, and proceed further. Again, programmers have a tendency to trust more inputs read from a file rather than inputs read from the user. Okay, so when you ask a user to input something, you check whether he entered the right value. If you want to work on these positive integers, you check whether he entered a positive integer or not, and all this stuff. But when you read something from a file, you trust that it's going to have the right information. So you don't really check what you're reading. So you just process what you read. So what if the attacker knows that and kind of messes up the contents of the file and makes your program to read some junk value? Okay, so then your program may crash. So it should not crash, right? So your program should be written in such a way that it checks what it reads from the file before blindly accepting that and processing. Okay. So these are also kind of testing strategies. So for security-based testing, you kind of go through, make your program go through all these things. You block access to libraries, you block, for the second thing, you change the corrupt registry values, you force the application to process some corrupt files and all those things. And then the last one is to manipulate the memory, disk space, or network. So this is also called as stress testing. In the sense that you see how your program behaves when it's subjected to a stressful environment, which means, for example, if the memory is not available in plenty, okay, so developers may take it for granted that this program is going to run in so-and-so environment where the memory is, say, going to be 1 gigabyte of RAM and all those stuff. What if the program is run at a memory which is very less compared to what it was assumed, right? So how does the program behave? Similarly, disk space. So if it's not going to have sufficient disk space, so that relates to virtual memory and all those stuff, how the program is going to behave. Similarly, the bandwidth. So if you're going to assume that you're going to download so and so bytes of information at a certain rate, and the network bandwidth is not really supporting it, this kind of application can still run properly. So all these things have to be tested. So how to conduct this attack or test? So again, I'm not sure that I introduced this term. Can anyone tell what's the difference between a cracker and a hacker? One of them is a really high-paying job.
The hacker is paying on that.
Huh?
The hacker is getting paid.
A cracker, I think, is getting paid.
So the cracker is breaking the software.
Right. The cracker is the one who really gets paid for breaking the software because he thinks from the attacker's point of view. So he really tests the software for security, right? So he thinks like a hacker. A hacker is a bad guy, and a cracker is a good guy. So he just tests the software to see if it can handle all those attacks.
But you see companies pay hackers to become crackers.
Is the other way? I'm not sure. I'll check and confirm, but one of the two is for good and the other is for bad. Okay, so we'll have to check. So don't take it for granted, but that's the way they do all these things. We have to think from an attacker's point of view. Okay? And then only you know how they think and how they will attack so that you can have the controls to protect from those attacks. Okay? So sometimes it's a catch-22 situation when the good people kind of put all the kind of security controls there, the attackers try to improve further and try to think of some novel ways of attacking further, right? So it's again, they will improve, you will improve, and so on. Okay? So, for example, how would you launch some attacks or test this under a stressful environment? When your application is running, run several other applications in the background and make them to download a lot of information. So your application doesn't get all the bandwidth it needs. So that's a stressful environment. And creating large files on the disk so it doesn't get sufficient disk space. And again, with RAM being a limited commodity, you run several applications again in the background. Your application doesn't get sufficient memory for the RAM. Okay, so it's again running in a stressful environment. Okay. So these are some of the strategies you can do with this stress testing. So I might have this as a question in the question bank for this chapter. Okay. Any question?
What is the stress
Testing. How do you test your software when some of the resources that it needs are not really available? Okay. So as a developer, you should not take things for granted that memory is going to be available so and so. So you should have some way of, your program should be able to handle when it operates in a resource constrained environment, right? Now, so we are going to focus more on the security of the application programs. So the previous chapters we saw about the operating system security. So we are now going to look at more at the application program level security and also certain non-kernel operating system programs. Like for example, the password command is not really an operating system program. Okay? It's like a user level program running at a non-kernel level, but it runs at a higher privilege. It can be run only by root. So how such programs can be kind of misused to launch attack. Right? So we're going to see each of this. We'll start with the linearization attack. Some of these are classical attacks. I have included them here just to illustrate the idea. They may not be really practical nowadays, but some of them are still very highly feasible, like the buffer overflow attack and stuff like that. So this is a very kind of classical attack, but still it is kind of something good to know. It illustrates a kind of a trade-off. Okay? Now, let's say you have, say, a password that you want to validate for a user. Okay? It could be a serial password with some numbers like this. Okay? Now, say user enters his password, right? So user enters his password, something like this, an 8-digit password. Now, how would you validate? You could compare it character-wise, right? That's what traditionally you do. Or even now, you compute a hash value of these two and you compare the hash values. And you can compare the hash values again still character by character. Okay. So, programmers are always interested in what? Making their program to run faster. Okay. So they compare character by character, or in this case digit by digit, and once they see a mismatch, like the 4th digit is a 2 here and this is a 9 here, they can say that this is not the right password. Right? So they don't need to compare with the rest. Okay? So the program can really stop and say you have not entered the right password. Okay? If someone enters, suppose, and how many character comparisons you are doing? You are doing 4 comparisons here, right? Isn't it? And if someone, say, enters something like this, how many comparisons you do and you can say they have not entered the right password?
What, 2?
Just 1. Compare with 1. So this is the right password. Okay? So you compare this 4 with 1 and you can say it's not the right password because once it doesn't match, there's no need to compare the rest. Right? So which means there is a small time gap. It takes 4 comparisons here, it takes only 1 comparison here. So the longer the match, the more the time it takes. So if someone enters the right password, it's going to take the longest amount of time to really validate that password. If someone enters the wrong password, it's going to terminate more quickly and say it is the wrong password. So this is the thing an attacker can make use of and launch what is called a linearization attack. So it's a guessing game still, but the guess is not done through a brute force approach. They can do more a linear approach. Okay? Because if, let's say, again going back to what we did in the password entropy and all those things, if you want to do a brute force approach and find this password, what will be the time complexity of it? How many passwords will you have to try at the worst case?
Big one?
Yeah, tell me the big O, or in this case you have the specific things. Let's say the digits, there are 10 numbers, 10 possible digits, right, or symbols, isn't it? And you have the length is going to be 8 symbols. This is the length, and the number of symbols is going to, the symbol set size is 10. So tell me from what you studied in the module 2 on operating system security, how many combinations of symbols you can have? 10 to the power of 8, right? So it's like n to the L, right? So this is a big O, right? The complexity of the brute force attack. Okay? We want to do it, so this is exponential, right? N raised to L. We want to do it more like a linear, which is n times L. So this is what I call a linear attack. So the idea is going to be very simple. Just stay focused on it. So what we are going to do, just take this thing. We'll start with a kind of what do you call, it could be all zeros. Okay. So you know that it's going to be 8-digit password. So let's say you know that. So the attacker knows that the password is going to be of 8 digits long. So what he does is he passes this as the password. It's going to of course compare the first with the first. It doesn't match, so it's going to break. He measures the time it takes for it to say that the password doesn't match. Okay. Then he's going to increase this to what? He's going to make it like 1, 0, 0, 0. Okay. And then it's going to compare these two. It's going to again say no. And then it's going to make it 2, 0, 0, 0, and so on. So everything else is the same. Okay. So it's going to change just the first digit. And do like this until, like, you can have only up to 0 through 9, right? Because you have only 10 symbols. Okay? So now what he's going to do is he's going to find how long it takes to get the error message for each of these 10 possibilities, right? Which one you think will take the longest time to get the error message?
The last
Last one? One that starts with a 4, right? Because that's the one. Why you said, someone said why it will be 4 that takes longest time?
That's the one that's correct.
That's the one that's correct, but it's not the entire password. Everything else doesn't match, right?
So I have to go and check the next one.
Right. So with the other ones, once the first one doesn't match, there's no need to compare the second character, right? Because the first one itself doesn't match. Whereas in this case of 4, the first one matches. So the program has to really compare the second digit, the 0 with this 5, right? So that's like 2 comparisons. Whereas for the other 9 passwords, you do only 1 comparison, right? Because for like 0 with 4, if they don't match, you stop. You don't even need to compare this 0 with 5. Similarly, 1 in this thing, you just compare 1 with 4, they don't match, you just stop. You don't need to compare the 0 with 5. So if you can measure the small time gap, right, you can notice that this one is going to take the longest time, right? So basically what you have done now, you have identified the first digit of the correct value for the first digit of your password. And you just repeat this to find the subsequent digit. So once you have found out it takes the longest time for 4, you fix that 4 is the first digit of your right password. So then what you do, once you fix it as 4, then change the second digit from 0. So the others could be still all zeros. Then change it like 1, 0, 0, 0, 0, then 4, 2, 0, 0, 0, 0, 0, and so on up to 4, 9, 0, 0, 0, 0. Okay?
Dr. Mick,
Yes.
you got me all the way to the point when you said 4 would take the longest time.
Right.
After that, I'm totally confused.
Why 4 takes the longest time? Okay, so what you're trying to find is the first digit of your password. Okay, so the first digit could be anything from 0, 1, 2, 3 up to 9, right? So you have 10 possibilities. Out of those 10 possibilities, I say 4 will take the longest time because with 4 being here as the first digit, it matches with the first digit over here. So your program is bound to compare the second digit in your password with the second digit over here. So you do 2 comparisons, whereas everything else you do just need 1 comparison.
Okay, I get you.
Alright? So now once you identify that 4 is the first digit, you try to identify second digit using a similar strategy. So now you subject the program to all its 10 combinations. Again, only 10 combinations, 0 through 9. Right? So find out which one will take the longest time. It will be for what? 4 with 5, right? Because that's the time, that's the instance where you have 2 matchings. So you have to do a third comparison. So whatever it is here is 0 compared with 6. They don't match, but you have to do 3 comparisons. Whereas everything else you do only 2 comparisons, right? So this is where you call the linear approach because how many possibilities you have? 10 possibilities for each digit and or each symbol, and you have 8 symbols over here. So instead of trying 10 to the power 8 symbols. At the worst case, you have to try only 10 times 8 symbols, right? So that's why we call it as a linearization attack. Okay. Is that clear?
How does the attacker know what is the set of symbols that he has to work with?
Of course, you have to know because, like, when you set the password, you are told you have to choose from a symbol set, right? It could be alphabet, it could be some special characters. So whatever its length is, you're given a standard or fixed or symbol set. It could have 128 symbols, it could have 200 symbols, but you know what is the size of the symbol set that you can choose from. And if, say, for example, you work with Unix, I believe the size of the password is fixed as 8. So if you enter a password less than 8, you are truncated with some characters. If you have what you call padded with some additional characters. If you enter more than 8, it's truncated. So the length of the password is always known. Okay. So it is very much possible to launch this attack. The only thing is you have to precisely time how long it takes to do those comparisons. So as a kind of simulation, so this is a simple C code which doesn't really time it that well, but this illustrates the idea where, for example, you want to validate, it could involve some alphanumeric, so it could be all alphabets, a combination of characters and numbers. So still you have, say, here the last character is enter or what is that, two line space character. So, but you have to only compare for the first 8 characters over here. Okay? So what are the character entered by the user in the command line? You compare it character by character and check if it is equal to. If once it becomes not equal, you kind of break from the loop. Okay? And if you don't break from the loop, then basically your I, the loop index, runs from 0 to 7 and is incremented to 8, and you check whether 8 is less than 8. So that's the time you really break from the for loop. And when you come here, we compare 8 equals 8. So which means you are really run the loop 8 times. So you have checked for all the 8 characters in your serial code or whatever you enter. And they match, because if something doesn't match like this, not equal to becomes true, then you would have broken from the for loop ahead of time, right? So if you come to this point, it means we have validated all of those characters and everything matches. Okay? So you see the serial number is correct. So this is a C, and I have a Java code that really can do some timing. So you can time at the nanosecond level in Java, and you can really simulate this attack. Okay. So let's say this is the password, the right password. Of course, as I said, the length of the password is fixed to be 8 in this case. So if a user enters anything less than 8 or greater than 8, you can right away say this is not the right password. Okay? So then you go through the password again, character by character. And what you do is, before you start anything, you have a begin time, okay, so that you can time all these things. And then once there is a mismatch, again it's not equal to, okay, find the end time, which means there's a mismatch, you have to stop your program. So find the time difference between the beginning time and the ending time, and that's the time it took for this program to run. Okay? Again, so we are doing it in nanosecond level so that it can be very precise. So exit from the program, which means you don't do the rest of the thing. Now you want to simulate the kind of comparison, because nowadays with all the processing capacity, this program can run in a flash of a second, right? So you cannot really time it. So what you do is you can make your program to sleep for a while. So after every comparison inside this for loop, you can make your program to sleep for a certain time. So I make it to sleep for, in Java, if you use the sleep method in the thread class, it takes an argument in milliseconds. So this means I'm making it to sleep for 100 milliseconds. So for every comparison, it sleeps for 100 milliseconds. So the more the number of comparisons it does, the longer it takes, right? Because once there's an unsuccessful comparison where the characters don't match, you break from everything and terminate the program. And otherwise you keep sleeping for every comparison or every successful comparison, and then only after all 8 comparisons are done you come out of this for loop. Okay? So once you come out, you find the end time and you print the time, how long it takes. So when you run this program, so you can run it like again trial and error. So this is not the only 8 of 8 attempts. You should have done what, 80 attempts, because 10 times 8, right? 10 possible digits and 8 characters. Well, I just show because I know what is the code. So here I am showing you because the correct serial number I have in that program is something like this. So for anything other than 1 is going to take a less time, right? So the password should start with 1. So if I start with 1, okay, so this is the default password I'm starting with, okay, and I start with the 1, so it takes 100 milliseconds. And then I keep changing this 5. Instead of 5, I can start with 1, 2, 3, 4, 5, and all start with 0, 1, 2, 3, up to 9. And when it is 4, it matches with this, and it takes like 200 milliseconds. Okay? So these are like nanoseconds, but if you convert back, it's almost like 200 milliseconds, 100 milliseconds, and so on. So sleeping time really dominates. Okay? And that's why you make it to sleep, because the number of times it sleeps is the number of successful comparisons. Okay? So 100, 200, 300, so for everything else you will get a smaller time, right? So for example, if you want to find the first digit say is something starting with 0, starting with 1, 2, 3, and so on, up to 9. Only for this case you will get 100 milliseconds. Everything else will be like 1 millisecond or very less time. So when you are trying to kind of do a cryptanalysis kind of thing, you will find for which it took the longest time. And that corresponding digit is the right value for that location. Okay? And repeat that for successive things. For example, in this case, only if the second digit is 4, it will take 200 milliseconds. The second digit is anything other than 4, it will take very less than 200 milliseconds. So among your 10 choice results that you get, find out which one will takes you more time. So that's how you narrow down to the right digit. Okay? So again, so this is a linear attack, where for every character you spend 1 leaf, for every symbol that you want to find you spend how much? The number of symbols in the set, right? And this could be done in C also, or C++. You want this as a project? No? I was thinking about it. I have one as a top tower attack as a project, that's project 4. This is quite easy. The only thing is, instead of doing this as a brute force, not a brute force, here I showed you have to really try it 80 times, because you have here what? 8 digits, and you could have, each digit could be anything from 0 to 9, right? So I show only 8 trials. You have to try 80 times, right? And so doing it like that manually, automated. Okay. So you have to really compare the time that you get out of the program, which one takes the longest time. Okay. So I'm thinking, yeah, I do myself the project and see whether it's or not, then only I assign to you. So I don't really just randomly assign and let you to do.
Because legally you might not be used to this.
I understand that. So if I have to really spend some time, then I think okay, student will take some more time. Okay. Bonus?
Yeah, bonus.
I have something else for that. This could be a bonus too. Okay, salami attacks. This came from a kind of, I think, the meat cutting shop, they use this term. it can be originated from there when you know, we call this what? Butcher. He cuts the meat, and if you want, if labor employee who works in such meat shops, they try to kind of steal some meat and sell it on their own, right? So if they cut a large chunk, they will just, and someone buys say some pounds, and this is not saleable, they'll try to hide it, and after a while it gets piled up, and they can sell it on their own. Okay, so that's the place from where this name came. But practically there was an attack on some banks, the bank employees, a developer, a programmer who developed some transaction software for the bank really launched this attack. Okay, so I don't know whether people have, you guys have thought about it. When you do currency exchange or any transaction, if things go beyond the second decimal, right? So currencies in US, you can go up to what? For example, $456.34, right? If you do some transaction and it goes to say something like this, what the banks do? Do they pay you those fractional cents? They can pay you to the lowest what, 1 cent, right? So they can pay you up to 34 cents. Do they pay 0.5 cents or 0.3 cents? Because this is really what? If you just talk with this, it means 0.3 cents, right? Because this is really the closest decimal they can get to. This is 34 cents, right? So with this, it's basically 34.3 cents. Can banks pay you 34.3 cents? They can either pay 34 cents or they can pay you 35 cents. They cannot pay you the fractional part of it, right? So when a banking software encounters such kind of transactions, alright, so the developer of the software, what he did was, he kind of diverted this 0.3 cents to his personal account, alright. So for every such transactions, he basically diverted everything after